So let's begin the class. This is lecture number 1, and we are going to deal with heat transfer in this lecture. I think this is thermodynamics lecture number 11 or 12, but we are going to deal with heat transfer in this lecture. Any idea about heat transfer? What do you mean by heat transfer here? What we are going to see is the mode in which heat is getting transferred. Now, if we just go back, the first chapter that we did was thermal expansion and calorimetry. In calorimetry, there was an exchange of heat between the system and the surrounding. In the next chapter, thermodynamics, also there was an exchange of heat and energy between system and the surrounding. Now, what we are going to see in this particular chapter is how this heat gets transferred between two bodies. Now, we have also seen that heat gets transferred only because of temperature difference. We have seen second law of thermodynamics, which says that heat can flow from higher body, a body at a higher temperature, to a body at lower temperature on its own. If you want to flow it from lower temperature to higher temperature, you need to do any work. That is your refrigerator. In this chapter, what we are going to see is how this heat gets transferred from one body to the other body, or from one system to the other system, or from system to the surroundings. And there are three different ways in which, three different modes in which heat gets transferred. What are the three different ways in which heat can get transferred from one body to the other body, or from one system to the other system? Yes. What are the three ways in which the heat gets transferred? The first way is known as conduction, which is the first thing that we are going to study. Then we have convection, which we may not study in much detail. And then we have the third thing, which is known as radiation. Again, coming back, heat is an energy in transit. Whenever it is getting transferred, it is known as heat. And how this heat is going to get transferred, we are going to study in this particular chapter. Sort of coming back to the first point, what is conduction? That is the first thing that we are going to study. What is conduction? What is conduction? Anyone, any idea what is conduction? What is conduction? Yes. Okay, first I will try to make you understand, and then you can note it down. Conduction is the mode of heat transfer which takes place basically in solids. This is the prominent and the predominant means of heat transfer which is present in solids. We will deal with conduction, all these three processes in detail. Right now, we are just going to have a look at a very brief look at what conduction is. Energy is passed from one particle to the other particle. In this mode of heat transfer, energy is transferred from one particle to the other particle. The particles do not actually move. It's only the energy which is getting transferred. And this type of heat transfer takes place in solids. Then the second mode of heat transfer is known as convection. You might have heard about convection currents. In the convection mode of heat transfer, the best example for convection is right now it's quite cold here in the northern part of the country, and you have a fire lit. You don't have to put your hands in the fire to get your hands warmer. If you are even far off from this fire, even you are putting your hands quite far from the fire, you will feel the heat. In this mode of heat transfer, the particles, the air particles which are near to that fire will get warmer. They will have energy, and that energy is carried away, and you feel that energy, and therefore you feel that heat energy. That is the mode of heat transfer which is known as convection. It takes place basically in liquids and gases. Convection also takes place in solid, but It's very, 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 very minimal. So you don't actually take it as a mode of heat transfer in solids, but it is the mode of heat transfer that takes place in liquids and gases. Then the third mode of heat transfer is known as radiation. Now, this radiation is the mode of heat transfer which is the quickest, because light travels, no, not light, heat travels in the form of radiation. It travels with the speed of light, speed of electromagnetic waves. Thermal radiations are also electromagnetic waves. Now, this type of heat transfer can take place in solid, liquids, or gases. You have a cup of hot tea kept in this cold weather. After some time, the tea will come to the room temperature. It has lost heat. No conduction, no convection. It loses heat by the form of radiation. So radiation is a form of heat transfer which takes place in all types of liquids, solid, liquids, and gases. This is a brief introduction of conduction, convection, and radiation. I'll give you a minute to note down these short points. Do it fast. Just note down the small points and we can move ahead. So we move ahead, and this is a table which is a very important table which summarizes all the points of conduction, convection, and radiation. Let me quickly go through them. Conduction, pink; convection, green; this blue. In conduction, heat flows from the hotter end to the colder end. The particles oscillate but do not leave their place. Here, the particles, they move from one point to other. Radiation does not even require any medium. Energy is transferred in the form of electromagnetic radiations. Medium is essential here for conduction, same for convection, but for radiation, medium is not required. Conduction is a slow process. Convection is also a slow process, but radiation is a very, very fast process. In conduction, the path is zigzag. In convection, also same zigzag, but in radiation, it is a straight line because heat is traveling as electromagnetic radiation. Conduction is a prominent mode of heat transfer in solids. Convection takes place in fluids. Anything that can flow, molecules have to move from one part to the other. It could be liquid, it could be gases. In radiation, it takes place in all types of medium, whether it's solid, liquids, or gas. Here, the medium will get heated up when heat flows. Here also the medium will get heated up, but in radiation, medium does not get heated up. These are all small points that can come as potential questions in your exam. So 2 minutes I'll give you to note them down. Note them down carefully. Now we will move ahead and see the first mode of heat transfer. And the first mode of heat transfer is known as conduction. So write the heading conduction. Conduction. Now, what do you mean by conduction? In this mode of heat transfer, the energy is transferred from one particle to the other particle. The particles do not move, but energy is transferred. Particles keep on oscillating or vibrating in their own positions, but energy gets transferred from one end to the other end. From one end to the other end. This type of heat transfer is known as conduction. The particles do not get dislocated from their positions. They remain in their positions. They remain vibrating in their positions. Energy gets transferred. Now, this conduction takes place in all types of matter, whether they are solid, liquids, or gases, but it is a It can only take place when particles are close to each other, and therefore this is the prominent mode of heat transfer in solids. In liquids and gases also conduction takes place, but the rate of conduction is very, very, very slow. So basically conductors are the mode of heat transfers in solid and particularly metals. In non-metals again, the particles are placed away from each other, and therefore in non-metals conduction is not a prominent mode of heat transfer. In metals, solid metals, particles are very close to each other, and therefore conduction takes place easily, and that is the mode of heat transfer. Do we understand this?
Yes.
This is the mode of heat transfer in solids. I'll give you a minute to note it down. Well, then, let us move on to the next heading, a very important heading which gets neglected. At times, it is known as steady state, steady state conduction. Steady state conduction. Now, what is this steady state conduction? Now, let me try to make you understand with this simple diagram. Let us say that this is a rod. I hope you can see this rod. This is a rod made up of a metal. Let me color it also pink. This is a rod. Okay. This is made up of a metal. A rod made up of a metal. Now, one end of this rod, let us say this end, is kept at a temperature T1, and this is at a temperature T2. So you can have boiling water on one end of the rod, and you can have freezing water on the other end, just to give you a um, analysis of, one side is at a higher temperature and the other side is a lower temperature. So you have boiling water on one end and you have freezing water on one end. They are doing their own thing. Now you connect a rod between the 2 points. Temperature T1 is higher than temperature T2, let us say. Now, as soon as you connect the rod, what happens? You only know. I don't have to tell you. What will happen when you connect the rod between 2 points or two bodies which are at different temperature? What will happen? What will happen?
So I didn't get it, sir.
What did it not get?
Oh, like where we'll have to connect them.
There is a fire burning far away from you, and you have a rod, and you hold the rod in one end, and you place the other end on the fire. What happens?
Heat is transferred.
From where to where? From where to where heat is transferred? Heat is transferred from the hotter end to the colder end of the rod. So slowly, you will start feeling that the other end of the rod, which is not in contact, only the first end of the rod is in contact with fire. The other end of the rod will also start to get heated up. Why does it get heated up? Because heat is getting transferred from the first end T1 end to the T2 end. Heat is getting transferred. Now, when the heat is getting transferred, if you take any cross section of this rod in the beginning, if I call this cross section as A, you take a small cross section, some amount of heat will be getting into section A, let us say Q1 or delta Q1. Delta Q1 amount of heat will be getting inside section A. Will the same amount of heat be leaving the rod? Will the same amount of heat will be leaving that section? the heat that will be leaving this section will be less than the heat which is entering the section. Yes or no?
Yes, sir.
Because some part of the heat will be utilized to warm up this section. So when this heat is getting transferred from end 1, let me call this end as end 1, to the end 2, initially in the beginning, some amount of heat will be absorbed in between the section. If I make a lot of sections like this, starting from section A, B, C, if I create a lot of sections like this, A, B, C, D, E, and so on, the temperatures of these sections will keep on increasing as time goes. Yes or no?
Yes, sir.
If I draw a graph, if I draw a graph of temperature from the hotter end to the colder end, the graph would look something like this. Yes or no? At the hotter end, the temperature would be high, and the colder end, the temperature would be less, and the temperature will slowly decrease. Yes or no?
Yes, sir.
Whatever amount of heat is entering one particular section, the same amount of heat will not be leaving that particular section. Yes or no?
Yes, sir.
This type of heat transfer is known as conduction is in variable state. This is, look, I will give you the note. This is the note for this. I will give you that note. Then you can note down that note and probably you will be able to understand it. So, what happens in the process of conduction? Every part of the rod will get heated up. Whatever amount of heat is entering a particular section will not leave that particular section because some amount of heat will be absorbed in heating up that particular section. Do we understand this? This type
Yes,
of conduction is known as variable state. So note down this and I will tell you what is variable state point wise as well. I'll give you 2 minutes. So we are dealing with something which is known as the variable state. What do you mean by a variable state of conduction? We are not going to deal any question in variable state, but just for your understanding, this is known as a variable state. What are the points about variable state that you must remember? Point number 1, temperatures of different sections are different. If you make different sections, temperatures of different sections are different. Temperature of sections. You understand the meaning of sections? Different sections.
yes, sir.
Temperature of the sections keep on changing with time. Keep on changing with time. Heat entering a section, heat entering any section is not equal to heat leaving that section. Why it is not equal? Why is the heat not equal? Some heat is absorbed in the section. some heat would be absorbed in the section, and that heat will raise the temperature of that section, and therefore the temperature of the section will keep on changing. Do we understand this variable state?
Yes, sir.
Now after variable state, what happens is you have something known as a steady state. After variable state, what you will get is known as a steady state. So what will happen in a steady state? After some time, the temperatures of these different sections will become constant. Temperature of different sections will become constant. They will not change with time. That state, what happens is whatever heat is entering any particular section, same amount of heat would be leaving that section. That state is known as the steady state, and no heat will be absorbed by the rod in between. Whatever heat leaves one section or one end of the rod, the same amount of heat will be reaching the other end, and no heat will be absorbed in the rod. Do we understand this? If
Yes,
I
sir.
have to draw this diagram, let me draw this diagram and try to make you understand. If this is the rod that I have drawn, the same pink rod, I am drawing again. Now when the rod comes in steady state, what happens? If I take any section of the rod, whatever amount of heat enters it, delta Q, the same amount of heat leaves it, delta Q. The amount of heat which leaves the end one, delta Q, the same amount of heat will enter or leave sec- uh, section B. That state is known as the steady state. Do we understand this? Yes or no? No, yes.
Yes, sir.
Everyone understands this?
Yes, sir.
Steady state. I'll give you 2 minutes to note this down. So, if we summarize, what do you mean by steady state? What are the points that you remember about steady state? Temperatures of different sections, are they same or are they different? If I take different sections, will the temperature of different sections be same or different?
Same, sir.
Temperature of different sections are different, because if it becomes same, then heat transfer will not happen. Temperatures of different sections are different, but the temperature of a section will remain constant. Temperature of the section remains constant with time. No heat is absorbed in the rod. Any heat entering a particular section will be same as heat which is leaving that particular section. This type of conduction, which happens after a long time, is known as steady state conduction. And most of the question that we are going to deal will be conduction in the steady state. Give you 2 minutes to note this down. Then we can do a small concept which is known as isothermal surface. This is a very simple and straightforward concept. Isothermal means same temperature. Isothermal surface. Isothermal means same temperature. Isothermal means a surface which has all points at the same temperature. Do we understand this? Yes or no? No, yes.
Yes, sir.
That is a isothermal surface. Any surface within a conductor where all the points are at the same temperature is known as a isothermal surface. Do we understand this? Yes or no? No, yes.
Yes, sir.
Okay, now remember, heat is always transferred or the direction of heat flow. That is the important point. The direction of flow of heat through a conductor at any point is perpendicular to the isothermal surface. Direction of flow of heat is always perpendicular to the isothermal surface. For example, if you have an isothermal surface like this, heat will be transferred like this. Do you see this? Yes or no?
Yes, sir.
If you have an isothermal surface like this, which is spherical, heat will be transferred like this. If you have cylindrical isothermal surface, heat will be transferred perpendicular to it. Isothermal surface. Anyone understands this? Yes or no?
Yes, sir.
I'll give you 2 minutes to note it down. Isothermal surface, then we have something which is known as the next important point, temperature gradient. Temperature gradient. Whenever someone uses the term gradient, there's something, the difference in something divided by difference in something. Gradient are normally calculated over time or length. Here the gradient is calculated over length. Temperature gradient, you might have heard about potential gradient. All these are calculated over length. So what is this temperature gradient? The difference in temperature or the rate of change of temperature with distance is known as your temperature gradient. If you have two surfaces whose difference in temperature is delta theta, this delta theta by delta x, the difference between the two isothermal surfaces is known as temperature gradient. Do we understand this? So you can see heat flowing, temperature gradient. Temperature gradient is nothing but change in temperature delta theta divided by delta x, or you can write it in differential form d theta by dx. How much the difference, how much the temperature has changed divided by what is the distance, that is known as the temperature gradient. Do we understand this? Yes or no? No, yes.
Yes, sir.
Now remember, as you go in the direction of heat flow, this is the direction of heat flow, temperature always decreases. Do we understand this? So in the
Yes, sir.
direction of heat flow, temperature gradient will be always negative because temperature will keep on decreasing. The SI unit, it is difference in temperature up divided by length. So SI unit becomes Kelvin per meter. Do we understand this? Yes or no? No, yes.
Yes, sir.
dimension becomes theta L raised to the power of minus 1. Now remember, in steady state, important point, in steady state, this temperature gradient d theta by dx is constant. It remains constant because the different sections will come to constant temperatures. The temperature gradient remains constant, becomes constant when the body comes, when the rod comes in the steady state. Do we understand this? That is the most important thing that you must remember about temperature gradient. Temperature gradient in a steady state is constant. When the state is variable, when the temperature of different sections are changing, temperature gradient is not constant. Do we understand this? Yes or no? No, yes.
Yes, sir.
I'll give you 2 minutes to note this down. Then let us move ahead and find out what happens in a steady state and how does heat flow. Let us again take the example. Let us again take the example of that pink rod of ours. This is the pink rod. This is the pink rod that we have. Now let us assume that this pink rod, one end of the pink rod is maintained at temperature T1 and the other end of the pink rod is maintained at the temperature T2. Let us say the length of this rod is L, the area of cross section of this rod is A, and this rod is in steady state. Do you understand the meaning of steady state?
Yes, sir.
And this rod is in steady state. Now, if this rod is in steady state, let us say heat is flowing and heat is flowing in this direction. That means I have taken which temperature more than which temperature? Temperature T1 is greater than temperature T2. Do we understand this?
Yes.
Let us say that delta Q amount of heat is flowing in this rod. Whatever heat is entering your section 1 at temperature T1, the same amount of heat will be leaving the section 2 because the rod is in steady state. Yes or no? No, yes.
Yes, sir.
Instead of calling temperature as T1 and T2, let me just change it because I will use T for something else. Let me call the temperature as theta 1 and theta 2. And let me call this as theta 1 greater than theta 2. Okay, that does not make any difference. Now let us say that delta Q amount of heat has flown from section 1 to section 2 in time delta T, small delta T. Delta Q amount of heat has flown, the rod is in steady state. Delta Q amount of heat has flown from point A, point 1 to point 2. On what all factors will this delta Q depend on? Delta Q will be proportional to what? The amount of heat that flows from section 1 to section 2 will be proportional to what? It will depend on?
Temperature.
It will depend on temperature or temperature difference.
Temperature difference.
It will depend on temperature difference, so it will be proportional to theta 1 minus theta 2. Anything else? It might be proportional to how much amount of heat has flown. Anything else? It will be proportional to. It's simple logic. If the rod is thin, if the
Length.
rod is thick, yes,
Length, I guess, sir.
It will be directly proportional to the area of cross section. If the rod is thicker, more heat will flow. The rod is thinner, less heat will flow. It will be proportional to the time, how much time that heat flows. If I put this rod for 5 minutes, less heat will flow. If I put it for 1 hour, probably more heat will flow. It is inversely proportional to the length. Inversely proportional to the length. Shorter rod, more heat will flow. Bigger rod, less heat will flow. It also depends on the material. If the rod is made up of silver, the heat flow would be different. If the rod is made up of iron, heat flow is different. If I put everything together, the formula becomes delta Q is equal to sign comes K A theta 1 minus theta 2 into delta T divided by L. Or I can write delta Q by delta T. It is the rate at which heat has flown. Delta Q by delta T, it is the rate at which it is flown, will be equal to Ka by L into theta 1 minus theta 2. This K, my dear friends, is a constant. This K, my dear friends, is a constant. And this constant depends on the type of material that you have. If it is a good conductor of heat, the value of K will be very high. If it is a bad conductor of heat, the value of K will be very less. Do you know what this K is known as? This K is known as coefficient of
Conductance.
coefficient of thermal conductivity. This K is known as coefficient of thermal conductivity. Do we understand this?
Yes.
This K is known as coefficient of thermal conductivity, and this formula is valid if the rod is in steady state. This formula is only valid when the rod is in steady state. In steady state, in steady state, if I find out between any two sections, the distance is dx or dl. The difference in temperature is d theta. This d theta by dx, which is what? Which is known as what? D theta by dx is known as what?
Uh, Change rate of change in temperature.
This d theta by dx is known as what? This is known as the temperature gradient. This temperature gradient is constant, and this temperature gradient will be equal to theta 1 minus theta 2 divided by L. This only happens when the rod is in steady state. So this is the formula for conduction through a rod in steady state. Conduction through a rod in steady state. K is known as the thermal of coefficient of thermal conductivity. K is known as the coefficient of thermal conductivity, and it tells us how good or how bad a conductor the body is. The unit of thermal conductivity, you can easily find out. The unit of thermal conductivity is calorie per centimeter second degree Celsius, or watt per meter Kelvin in SI units. Its dimensions, you must remember the dimensions. Its dimensions are m L T minus 3 theta minus 1. So I will give you 2 minutes to note down these points. Note down these points. I'll give you 2 minutes. K is known as coefficient of thermal conductivity. We have already seen that there are a few points that we have seen. What is the SI unit? What is the dimension? 2 or 3 more points. You must remember the value of K only depends on. So you continue. The value of K only depends on the material of the conductor. It depends only on the nature of the material of the conductor, nothing else. For perfect conductors, the value of K is infinite. And for perfect insulators, the value of K is 0. Do we understand this?
Yes, sir.
Substances which allow heat flow, they will have large conductivity and therefore their K will be large. Do we understand this? Yes or no?
Yes, sir.
If the value of K is large, that means it is a good conductor. If the value of K is small, that means it is a bad conductor. Yes or no?
Yes, sir.
So just note down these points. Some of these points may appear in your exam, and that time you must not be fine lagging. The conductivity of pure metals decrease with rise in temperature. Remember, they could give you a graph and they could ask you which is the graph for metals. You must be good enough to tell which is the graph for metals. So these are all the points about thermal conductivity given in one screen. I'll give you 2 minutes to note down these points. And let's move ahead and I'll give you a couple of problem. I hope you can solve it so that we can move ahead quickly. This is the first problem coming for you. Simple problem based on simple concept. Uh, in every problem, it might not be mentioned that the rod or the body is in steady state. We have to move. We have to assume that the question is made on steady state. Do we understand this? Yes or no? So this is the first question. One face of an aluminum cube of h 2 meters is maintained at 100 degrees Celsius and the other end is maintained at 0 degrees Celsius. As I told you, boiling water and freezing water. All the other surfaces are covered by adiabatic walls. Why they are covering it by adiabatic walls? So that there is no heat transfer by radiation. Radiation is the third part of this chapter. So the only mode of heat transfer here it is possible is by the mode of conduction. Do we understand this? Yes or no?
Yes, sir.
Find the amount of heat that flows through the rod in 5 seconds. The thermal conductivity of aluminum is given to you, and you have 2 minutes to give me the answer. Well, I think I should do this. So, the straight away formula, what you have to apply is delta Q by delta T is nothing but K into A by L into theta 1 minus theta 2. Delta Q is the amount of heat. That is what you have to find out. Delta Q divided by time is given as 5 seconds. K is given as 209 or everything is given in SI unit. The side of the cube is edge of the cube is 2 meters. So the area of cross section will be 2 into 2, 4 meters square multiplied by 4 multiplied by the change in temperature. Whether you call it in degrees Celsius or Kelvin, it is same. Divided by length is 2 meters. Multiply it, divide it, and you will get the answer. Delta Q, the answer given to me is how much? 209 kilojoules. And that is the answer that I was looking for. Did any one of you get this?
Yes.
Okay. If you got this, then I'll have to move on to the next question. The next question comes on your screen now. Heat is flowing through a rod of length 50 centimeters and area of cross section 5 centimeters square. Its ends are respectively 25 and 125 degrees Celsius. The coefficient of thermal conductivity is also given. Something something. What is the temperature gradient in the rod? Assuming it to be in steady state, I'll give you a minute to do it. It is option A. It's very simple. To find out the temperature gradient, you just have to find delta theta by delta x. Change in temperature is 100 degrees Celsius, 50 centimeters is the length of the rod. I don't know why you have taken so long. It is 2 per degree centimeter, and that is the answer that we were looking at. Do we understand this? Yes or no? No or yes?
Yes.
The next question comes on your screen now, and I expect a quick answer. Consider two rods of same length and same specific heat. Conductivity is K1 and K2. Areas of cross section A1 and A2. Both having temperatures T1 and T2 at their ends. The rate of heat loss due to conduction is equal. Then which of the following option is correct? Option A is absolutely correct. You know, delta Q by delta T is K A by L into, let me write it as delta theta. Delta theta means change in temperature. Now, rods are of the same length. Specific heat will not matter. Their conductivity is K1 and K2. Area are different. Temperature difference is same. So this is same. Rate of heat loss is same. So everything is same. That means K into A will be a constant. So K1 into A1 becomes equal to K2 into A2. That is the answer that is the correct one. Do we understand this? Yes or no? No or yes?
Yes.
Then comes this one. And I'll give you 1 minute, 2 minutes to solve this one and let me know the correct answer. So the ratio of heat transferred is same. That means delta Q by delta T. If I write delta Q by delta T, which is nothing but K A by L into delta theta. This delta Q by delta T is same. That means this is same. The difference in temperature between the two things is same. Same material, so K is same. Same cross sectional area, so A is same. Oh, you have to find dq by dt. Sorry, I did that same. So you have to find dq by dt. The rate dq by dt will be proportional, inversely proportional to L. So delta q in the semicircle divided by delta q in the straight rod will be length of the rod divided by length of the semicircle. The length of the rod is 2L. No, sorry, 2R if you want to write, where R is the radius. So let me write it as 2R divided by pi R. That is the answer that I am getting, and the answer I am getting is 2 is to pi. That is the answer that we are looking at. Do we understand this? Yes or no? No or yes?
Yes.
Do we understand how this is done?
Yes.
This is a question from a previous year IIT. It might require some calculations, but you can solve the question without the calculation in terms of algebraic and give me the algebraic answer. I don't want you. I don't want you to. I don't want you to get involved in the calculation. So the room is maintained at temperature 20 degrees Celsius. You can call that temperature as theta. By heater of resistance, you can call this as R. You can call this as the voltage V. Area of the window is A. Thickness of the window is, let us say, L. What is the temperature outside? K is given as K, and J, whatever this J is, this is known as the mechanical equivalent of heat. It is used to convert heat from calories to joules and from joules to calorie. This is it. Let's see if you can give me the answer in this form. I'll give you 2 minutes. Everyone understood the question? Yes or no?
Yes, sir.
2 minutes you have. So when will the temperature of the room remain constant? When the amount of heat given by the heater is equal to the amount of heat which is entering through the window. Amount of heat which is given by the heater is electrical thing. It is V square by R. It is the power multiplied by the time, let us say dt. This is the amount of heat which is given by the heater. That must be equal to the amount of heat which is conducted through the window, K into A by L, which is the thickness of the conductor, into the change in temperature, difference in temperature, 20 minus theta multiplied by dt. dt and dt getting cancelled. This K is given in calorie per meter. So you have to convert it into joules. So you can now multiply this by the constant J, and that will be your answer. You can find out the value of theta from here by doing the calculations. So the value of theta will be 20 minus theta. 20 minus theta will be equal to V square L by K A R J. So taking it to that side, theta will be 20 minus V square L by K A R J. It's not 20. I've given it as theta, right? Oh, I've called this as, let me call this as theta 1. Theta 1. Theta 1. Theta 1. Oh, mistake. I will call this as theta, and the temperature outside, let me call it as phi. So this will be multiplied by theta minus phi. So this will be equal to theta minus phi. Do we understand this? Yes or no? There were two temperatures given. Do we understand this? Yes or no?
Yes, sir.
Sure?
Yes, sir.
One more question here. This type of question can come in a JEE main or advanced. So this is the next question. A point source of heat of power P is located at the center of a spherical shell of radius r. The material of the shell has a thermal conductivity K. If the temperature difference between the inner and the outer shell is not to exceed T, the thickness of the shell should not be less than what? I give you 2 minutes to give me the answer. So how are you supposed to do this? Remember, this is a thin shell. So you can draw this thin shell like this. It's a very thin shell. And it is given that the radius of this shell is R. We can assume that the small thickness of this shell is delta X. Delta X. So this is a point source placed here. The rate of heat given by this point source, the power is P, and that is the energy per unit time that has to be conducted. So that will be equal to K multiplied by the area. Area of this shell is 4 pi r square divided by delta x, which is the length or the thickness of this shell, multiplied by the temperature difference. So from here you can find out the value of delta x, K 4 pi r square T divided by P. So the correct answer happens to be option B. Do we understand this? Yes or no?
Yes, sir.
Did you get the answer for this one? Do we understand this?
Yes, sir.
Can I give you the next question?
Yes, sir.
This is the next question, and I expect a quick answer. There are three thermometers, one in contact with the skin of the man, other in between the vest and the shirt, and the third is between shirt and the coat. The readings of the thermometers are given. The vest and the shirt are of the same thickness. The ratio of their thermal conductivity is. Give you 2 minutes to give me the answer. The readings of the thermometer are this. Vest are of same thickness. What is the ratio of their thermal conductivity? So basically you just have to apply the formula delta Q by delta T, the rate of heat flow. Whatever heat is flowing from the skin to the coat, that is same. Yes or no? Do we understand this?
Yes.
Ka by L into delta theta. Now this is same. Length and the area of cross section are also same. Yes or no?
Yes.
Length and area of cross section are same. That means K1 into delta theta 1 will be equal to K2 into delta theta 2. Yes or no?
Yes.
K1, let me call it as shirt into delta theta between the shirt and the temperature is 5. Yes or no?
Yes.
Into 5. That must be equal to K of the west multiplied by the difference in temperature is 3. The ratio of thermal conductivity of west, K west by Ks, is 5 by 3. So that is the answer. Do we understand this?
Yes.
No, vest and the shirt and the coat. Skin, uh, vest and the shirt. The first one is the vest. So this is K vest. The first clothing is vest. So this is K vest. And the second clothing is shirt. So I have written it wrongly. K shirt. So K west by K shirt is not 5 by 3, but it is 3 by 5. I've written it in the reverse order. The first thing that is wearing is the vest, then the shirt, and then the coat. Do we understand this? 3 by
Yes.
5 is the answer, my dear friends. We get this, yes or no?
Yes.
I had written it in the wrong order. And that is why my answer was coming reverse of what was given in this. Now, what we had seen is the flow of the conduction of heat in steady state. If it is was not steady state, then the temperature gradient would not have been same. So you can find a relation, the differential form of equation. So you can write the differential form of equation. Differential form of equation. The differential form of equation of this can be written in this way: dq by dt, the rate of flow of heat, will be Ka into d theta by dx. Do you understand the meaning of this?
Yes.
With a negative sign it is written because in the direction of heat flow, the temperature decreases. Do we understand this? So this is the differential form of the same equation. Now this form can be applied whether the heat conduction is taking place in steady state or whether it is not taking place in the steady state. Do we understand this? Yes or no? No or yes?
Yes.
Okay, I'll give you a minute to note this down. The next heading that we will write will be thermal resistance. Thermal resistance. Now, what do you mean by this thermal resistance? Well, again, let us go back to our rod. This is our pink rod. It has been helping us a lot right from the first minute. Now, this rod is maintained at temperature theta 1 and theta 2. Now, because of this difference in temperature, what happens? Heat flows. Yes or no? And the amount of heat that flows in a small small time, the rate of heat flow delta q by delta t. Why does this heat flow? This heat flows because of difference in temperature. Yes or no? Yes or no?
Yes.
Sometimes this rate of heat flow is also known as heat current. This rate of heat flow is also known as heat current. Why it is known as heat current? Now, if I just take you back to this analogy, do you know what is this?
Resistant.
This is electrical resistance whose resistance is R. Now, if I have this point at voltage V1 and this point at voltage V2, because of difference in voltage V1 greater than V2, electric current flows from point A to from point 1 to point 2. Yes or no?
Yes.
The electric current that flows can be written as V1 minus V2 by R. Yes or no?
Yes.
This current flows because of difference in potential. So potential difference. Heat can also be treated as a current. Heat current flows because of difference in temperature. So I can write this delta Q by delta T, which I can write as IT, heat current, thermal current, IT or IH, heat current, can be written as theta 1 minus theta 2 divided by RH. Oh, let me not write it as H because H gives me heat. Let me write it as T. So T will give me thermal. So I can write this IT thermal current same as RTH. Now this RTH will do a similar job as this resistance the resistor ka resistance is doing an electric current. Yes or no?
Yes, sir.
Now write the formula for if I write the formula for heat current delta Q by delta T, that was Ka by L multiplied by theta 1 minus theta 2. Yes or no?
Yes, sir.
I could have written this in this fashion, theta 1 minus theta 2 divided by L divided by Ka. Yes or no?
Yes, sir.
This term L divided by Ka came is also known as the thermal resistance of this rod. So this rod can now be treated as a resistance whose thermal resistance is given by L by Ka. L is known as L is the length of the rod, K is the coefficient of thermal conductivity, and A is the area of cross section of this rod. Do we understand this? So this RTH L by K is known as the thermal resistance. We understand this? Yes or no?
Yes, sir.
And it is exactly similar to the resistance of a resistor. Resistance of a resistor can also be written as L by sigma A. This sigma is known as the conductivity or electrical conductivity of the resistor or the material of the resistor. Do we understand this? So this and this resistance are actually exactly similar to each other. Do we understand this? This
Yes,
concept
sir.
is known as the concept of thermal resistance. Do we understand this? I'll give
Yes,
you
sir.
2 minutes to note this down. Then you can draw this table and understand the similarity between electrical current or electrical conduction and thermal conduction. As you can see, both are exactly similar. In electrical conduction, current I is dq by dt, heat current is the rate of flow of heat. Electrical current is V1 minus V2 by R. Do we see this? Yes or no?
Yes, sir.
Thermal current is theta 2 minus theta 1 minus theta 2 by R. This electrical resistance is rho L by A or L divided by sigma A, where sigma is known as your conductivity. Your thermal conductivity is L by Ka, where K is known as the coefficient of thermal conductivity. Both are similar things. Do we understand this? Yes or no?
Yes, sir.
I'll give you 2 minutes to note down this table. Note it down. Okay, then we will meet in the next class and go ahead with this because the time is over. In the next class, we will see what things we can do with this thermal conduction and electrical conduction. We will be taking examples and seeing how this is same to electric current. So take care and I'll see you tomorrow. Bye bye.